Good evening and good morning. Uh, Welcome to the webinar session in the KIAT-Georgia Tech Semiconductor Electronics Center. Today's speaker is Dr. Sehoon Ha. He is assistant professor in the School of Interactive Computing at the Georgia Tech. Before joining Georgia Tech, he worked as a research scientist at Google and Disney Research Pittsburgh. His research focuses on robotics, computer graphics, and machine learning, particularly on developing intelligent and physically grounded model for robot motion and control. He leads the Intelligent Machine Dynamics Lab at Georgia Tech, where his team explores how robots can learn to interact more naturally and effectively with the physical world. Um, let's welcome Dr. Ha.
All right, thanks for the kind introduction, Dr. Kim. Today, I would like to discuss the basically ongoing research project in my lab under the title of the Guided Reinforcement Learning to Learn Interactive Motor Skills. These days, I've been interested in applying what I've learned from the computer graphics community to develop natural and effective robot controllers. All right, let's get started. So basically, I've been interested in at control of things. So it can be either abstract system or the virtual human computer game. But of course, these days, I'm interested in controlling robotic creatures, which is so exciting. And of course, it also has some useful applications. So the people, had dreamed about autonomous robot for a long time, I believe. For instance, actually, one of the earliest imagination would be Talos from Greek mythology, which was the spoken around the BC 400, which is quite a long time. Of course, and at that time they dreamed about the bronze giant who can protect the island autonomously. Of course, I'm pretty sure that this is not the earliest the imagination about autonomous robots. I believe someone had dreamed about it a lot earlier than that. And these days, we are also interested in developing autonomous agent who can talk to us, who can leave us or play with us. That will be our long goal for many of the roboticists. Then what about the implementation? One of the impressive implementation is actually from the Leonardo da Vinci. Yes, the Leonardo da Vinci. He developed a mechanical knight who can move its joints accordingly. Of course, there's not that much of the about the actuation, but still it has nice mechanism. And then we live in the 2025, and we live in good time, particularly for roboticists. And if you go to some exhibition, then you can see that there are robots are walking around, grab a box. Of course, it's still a little bit of the demo setting yet, but still they can contribute a lot. I believe they has great potential to improve our life. It's the same for us. Our lab is also interested in developing a more intelligent robotic agent who can help make our life better. And that's our lab's aim. We aim to develop intelligent assisted robot that can perceive surroundings and interact with them. What does it mean? So actually, here's my favorite example. Here's a dog who's trained to fetch a beer. I really like this because he not only just move around, he can interact with the environments. Of course, there's no provided map, and I believe he only used his onboarding sensors, and then handle everything gracefully and nicely. So this is one of the example I really like to use. Similarly, I believe if we can develop such an autonomous robotic agent, we can do a lot of things. For instance, one example would be last mile delivery, who can deliver the items to our home, or that they can be just a lifelong companion, talk to us, interact with us. Maybe they can be assistant the humans, I guess. And then research-wise, I've been interested in deep reinforcement learning, deep RL, for many years, actually. It's been popular framework for robotic agent because it helps us to make the best decision in terms of the sequential problems. The other deep reinforcement learning finds an optimal agent that maximizes the cumulative reward via environment interactions. There's an agent and there's environments. Then agent takes an action to the environment, which give us the next state. And also it also evaluate the goodness, effectiveness of the robot. And then we can develop we want to, from the state, we want to develop the decide what is the best action, which is typically modeled as the neural network. And then the deep reinforcement learning has emerged as an interesting tool for robotic agent. One of the impressive work is this work from the ETH and NVIDIA, which shows the massively parallelized deep reinforcement learning. And then it's only limited to simulation. I've been also interested in how we can use the real-world data to make more robust agent, like who can overcome this kind of the unstable platform, which is unseen during training, as well as the stepping down from the stair. Or by combining simulation pre-training and the real-world training, we can transfer the nice simulation behavior, such as this bipedal balance, and then we can achieve it in the real-world hardware. So far, it sounds the RL sounds like a magical tool which can solve all different problems. Of course, there are some disadvantages. Despite the recent success, deep reinforcement learning is slow because it needs to leverage expensive simulation, which may be able to. We can parallelize them using the GPU, but still they are quite expensive. And if you start to consider real world experience, it becomes more and more expensive. It's also inaccurate. Even though we put a lot of effort on modeling accurate simulation, it is inaccurate because we need to make a lot of simplification. It cannot capture a joint slackness like bending or the electronic dynamics. There are a lot of missing pieces. And also they are less scalable because of the parallelization requires the massive data exchange, particularly compared to the supervised learning, which load a massive amount of data and do the learning in a static setting. But deep reinforcement learning is more like shooting the moving target. You need to constantly exchange the data. Finally, it is vulnerable to local minima because it always prefers the data near the current policy. So always you need the up-to-date data rather than the leveraging the historical data. So let me highlight the one of the challenge. Here's you may think, oh, maybe how about making simulation really accurate, but it cannot work. Let us imagine a problem with the learning a policy to manipulate the bread. A state-of-the-art FEM will be super expensive. This looks nice, but this may not. Doesn't capture the exact, the finite element level accuracy. So it may look the same, but that's not the. We cannot guarantee the exact simulation. It's too expensive. Therefore, those challenges enforce us to leverage a tremendous amount of samples to stabilize the policy gradient during the deep reinforcement learning. Uh, then our research usually start from here. Can we do better? than just generating the more just better than the rather than just generating more and more samples. Can we do any better? So here are some, I group some of our ideas. So basically, we believe deep reinforcement learning must be properly guided to overcome those disadvantages, such as expert policies. We as community, we have been developing a lot of expert policies, like a model-based controller, and they should have some nice insight about the problem, so they can be synergetic with the existing deep reinforcement learning or the motion capture data. A human's motion is actually the great source of the inspiration. They tell us how to maintain balance or how to maintain the interact with the environments. So maybe learning from the human motion is a good idea. Of course, these days, the leveraging foundation models, such as the large language model, would be a great idea because by reading the digesting internet scale data, they contains a lot of information. So today, I would like to discuss our research project in these three groups. All right. First is expert policies. Let me start from here. This is the project I developed. I started with the, this started with the, my KIAT. So basically, here the key idea is that how we can combine model predictive control with the deep reinforcement learning to obtain a nice metric gate without the while still taking the advantage of the deep reinforcement learning. So we propose an imitation fine-tuning strategy to first, basically we take a model predict controller, we use the imitation learning to bake that information into the policy, and then we improve the style of the we improve the performance using reinforcement learning based fine-tuning. Then this improved from the perspective of the model predict control, it improved the performance, or from the perspective of the reinforcement learning, it definitely improves the style. It allows us to achieve better, more stable these metric gates. Here's an example. This is the original performance of the original model predictive controller, but then if we fine tune the policy using our what we proposed, then we can achieve the much more better robustness. After that, we thought, oh, maybe this entire pipeline is a little bit generic. It can be applied to other applications. So okay, there might be we can apply to the humanoid robot, and then yes, it worked. Of course, we needed to guide a little bit more. Basically, we propose the preservative fine-tuning rather than unrestricted fine-tuning. But then this is the performance of the model-based controller, which works at the top of the 0.5 meter per second. But then our fine-tuning allow us to work at the 1.5 meter per second, which is the 3 times faster than the baseline. We also take the humanoid robot to the outside. This is the sandy terrain test that we walk in the sandy terrain, and then robot was able to walk nicely on this irregular surface. We turn around and walk back to the original position. All right. So then, okay, is model-based controller be the only option for expert? We believe not. We believe the previously trained policy can be also the expert. So we developed this cascaded compositional residual learning. Basically, we take the original scale and fine tune it for more complex scale. Here, we hypothesize that a complex skill can be learned as the perturbed version of the simpler skills, like the turning left is the perturbed version of the walking straight, or the interactive reach is the combination of the open door, left, right, and crawl, something like that. So we then by doing constraint perturbation to the original skills, we can learn more progressively learn more and more challenging motor skills. By combining this all of them, we can create a nice skill graph, which can be work as the then at the end we can develop very nice interactive behavior. We use the framework of the multiplicated composition policy. So for the existing skill library, we freeze them while there we learn two components. First one is the three component actually, syntactic goal network. And then there's also weighting network, which kind of the weights the which expert we want to activate at this moment. And also there's a residual policy, which generates the a small portion of the perturbation to the existing skills. And then this allow us to learn interesting perturbation skills, interactive skills, such as the box pushing object to the target location. These days, I've been also working on another project, which is the learning from the trajectory optimization as well. Here, we take the trajectory optimization as the expert, and we train the box carrying policy. Or this is the opening the door. We open the door, and then we can walk in. And then we can draw something on the board using trajectory by learning from the optimized trajectory, and then we can also wipe those things. All right. I mostly talked about the have talked about the control, but same philosophy can be also applied to the navigation as well. Here we learn to navigate the sidewalks in outdoor environment. Here the goal is that not just walk without collision. Our goal is to understand the semantic of the surroundings and follow the given waypoints. Here we take the learning by cheating approach. It consists of the multiple steps. First is the learn a capable teacher policy with the privileged information. Here, the privileged information is that refers to the information that is usually not available to the robotic agents, such as the bird eye view from the sky, so that it can see everything. And then this allows us to learn the nice behavior first. And then we clone the learned behavior to a student policy with the realistic sensors, such as the LiDAR or the egocentric viewpoint cameras. And then we deploy it to the real world. In this project, we deploy the robot to 6 trails in the outside of the outdoor of the Atlanta, including the campus. And then actually we were able to travel more than the totaling the 3.2 kilometer of the course with a handful of the failures. However, I believe that it is better for community to share the failure cases as well, because that's the spirit of the healthy robotics community. We oftentimes see failing semantics or the drifting orientation. One of the interesting examples was the sloppy driveways. Because in our simulation environment, we didn't have any driveways. So actually, every time it sees driveways, it confused a little bit and it thinks that's the right way to go. But anyway, at the end, we did not hurt the robot. We were able to complete all the experiments, so it was very nice. And then from there, I believe we can apply to the new applications, such as the using quadrupedal robot as the robotic guide dog. We can do wayfinding as the human robot team and avoid guide the user to avoid the collision with the environments. And then here, successful human guidance lies at the learning profile interaction model. One common model is that there's just a rotating rigid body, which just assumes that robot is following the robot from the behind. But that's not the case if you take a look at the actual team of the human robot team of the blinded people and the animal guide. It's a little bit closer to the rigid harness model, which assumes that the human is really always at right next to the robot. But then it's fixed distance between it usually assumes the fixed distance, and then usually there's a more flexibility in the real world. So in that sense, we develop a concise mathematical model, delayed harness, to better capture the human-robot interaction. It first here are first let's assume there are the initial human and robot locations, and then the robot takes an action first, such as the let's say the move forward, then the robot moves the forward first, and then we know that this is the rest position for a user with a harness. It maintains the distance between the same distance between the robot and the guide dog, robot guide dog and the human. But in reality, usually there's a delay in terms of the interaction. So rather than snap right away into the rest position, a human goes toward the rest position with delay. There's some delay. And then it changes the relative position between the robot and human a little bit. Also, we implement the another safety predicate. Basically, there we take the convex hull of the human robot team and make sure that if you when you take the next action, it does not collide with any of them. And then if we expect some collision, then we filter out so that we do not have any. We can eliminate the potential collisions. And then this work was introduced at the quarter 2023 under the title of the Transforming a Quadruped into a Guide Robot for the Visually Impaired. You can navigate. This is our cloud computing building, which has a nice, unusual curvatures, and then it can also but still it can successfully guide the user to the target location. Here's another work, which is basically generating the motion in the simulation. Our key idea is that we generate a lot of feasible motion plans using trajectory optimization, and then we build a big part of the motion library. And then we build one auto-regressive neural network planner so that it can liably find a nice trajectory in the unseen environments. This is more like a work for the simulation, but for the given waypoints, rather than generating just the root movements, it generates the full body movements, which is tailored to this quadrupedal robot. And then it can go to the target position. All right, that was the first section, expert controller. And now I would like to move on to the motion capture part, how we can leverage the motion capture, motion data, human motion data to develop better robotic controllers. So here's actually one of my favorite work. which trains the basically quadrupedal robot to imitate the dog motion capture data. And this was the from the my fellow researchers when I was at Google. I really like this work. And then something disappointed for me was there's not that much of the dog mocap data. Of course, a dog cannot do that many things compared to the human, and also it's a little bit difficult to direct dogs what to do. So actually that makes sense, right? Yeah. So it has very limited set of there are only limited set of the dog motion capture data. But think about this. We have lot larger human motion data. I can name the already 2 to 3 huge motion capture data, which it consists the thousands or the 10,000s of the motion capture data. Then how can we leverage those larger scale of the motion data? Then I believe the here's our. I think it was the start was a little bit goofy. We thought, okay, maybe we can retarget the human motion into the robot motion. Here the action is a little bit exaggerated. At this time, the emotion retargeting module was a little bit primitive, and then but still it dog is trying its best to follow the what human is doing, and then note that everything is teleoperation. He doesn't know what to do, but it's more like a live control of the motion. Then, if you think about how we can approach this problem, we did exactly what they came to our mind first. We first capture the human motion using the consumer grade motion capture motion capture system, which is the Kinect. And then from the paired motion data set, we retarget it to robot motion. And then we train the imitation policy using deep reinforcement learning. And then we deploy onto the rear quadrupedal robot. That's it. There's no secret magic. It's just the kind of the proof of concept. But we wanted to know whether this is possible or not. And this is as far as I know, this is the one of the early work as the using the paw as the end effector. All right, then what I really like another interesting result for me from this project was that it can even walk. And then this walk in this walk, it doesn't know it's walking actually there. It just try to imitate the human operator, and as a result, it can walk forward. This is really interesting part of interesting part of this motion retargeting project. And then at the end, we were able to the user was able to push the box to the target position. All right. Then we thought, okay, that was nice, but then the motion retargeting was too primitive. It cannot consume the large amount of data, and actually, the generating data itself is very cumbersome. So what we did was we leveraged the adversarial learning. We pre-trained the very concise robot controller. We call it motion prior from the handful of the robot data set, which give us embedded space of the Z. Basically, by tweaking the Z, we can control the robot. It's a very a small number, and then now we apply the generative adversarial learning. Here, our generator takes the role as the motion retargeting model. It takes the human motion as the input, and then ups the Z, which is the the knob for controlling the robot. And then our discriminator checks the if synthesized motion looks similar to the what we had in the robot data set, so that they can, they look natural and being capable, being feasible in terms of the robot's perspective. And then this allow us to develop the lot better motion retargeting. Here's the result of we retargeting the human wiping motion onto 3 different robotic platforms: the legged manipulator, the spot robot, hexapod, daisy robot, and mobile manipulator, stretch robot. You can see that they all look different. There are some, they use different end effectors, but still they use what they have, or what they can do. They wipe the war in their own ways. And then at this moment, we start to think, okay, can this be transferred to the real world robot? And the answer was yes. We take the motion and then we deploy onto the hardware, and then it can be deployed to the deployed nicely. This lightsaber motion was successfully deployed. And then it was pretty wide, a little bit wider than more wide than we expected, but still it didn't lose balance. All right. And then at this moment, we start to think, okay, that was nice, but still requires the original robot motion prior, which is actually not only cumbersome, but also limits the capability of the robot. So in that sense, we develop we develop the guided unsupervised reinforcement learning approach. So basically, we drop the needs for the we drop the needs for the having motion prior. So policy generates the action to imitate the given human reference motion, just like previous the generator. But then what we do next is that we train the R to H, basically Roman to human mapper, and also as well as the human to robot mapper. So here our philosophy is that, hey, once you retarget the human motion onto the simulated robot motion, and then it must be able to translate into the original human motion. And also at the same time, the reconstructed human motion should be able to reconstruct it to simulated human motion as robot motion as well. So we call this as the cycle consistency, which is inspired by the image transformation domain. It's from the computer vision community, but we take that concept and we transfer that concept onto the this motion retargeting problem. As a result, we were able to retarget a lot of motions, ranging from dancing, hopping, or the running, and then also a lot more, including a wide range of the motions was able to transfer to the other robots. Okay, but then, okay, it looks nice, but then why do we need this? Basically, it serves as the connector to the existing foundational human motion models. For instance, there are existing text-to-human models from the fast walking, they generate this kind of the human motion. And then we don't need to retrain the robot foundation model for different robots. We can just reuse the existing foundation model for the human, and then we just retarget the generate human motion. This allows us to very concise interface to the existing foundation model. All right, then we extend this for further and further scenarios. Here, our project is about the capturing multiple agents interaction. The key concept is that rather than learning, so there's a concept of the interaction graph, which measures the distance between the important body nodes. But then when you retarget it, this full interaction graph is too dense to be transferred to robot with different morphology. So we learn a concise embedded interaction graph and transfer it to their various morphologies. We first pre-train the motion prior for different characters, and then there we embed, we find what is the most important interaction using the cross attention model. And then once you identify, oh, this is the key interaction between these two characters, then we ask the robot to robots or the different age combination of the agents to imitate the most important crisp part of the interaction. This allow us to transfer this kind of the interaction. This is the sparring motion between the two characters. Human motions are basically kinematic. They are the motion capture data. On the other hand, the robot motions are physically simulated. You can see that they are not exactly the same, but you can see that they conveys the similar semantics from the human motion. This is what I meant by the transferring interaction. All right. Here's another work that we learn to here we aim to learn the how human interact with the heavy objects. We learn we define the concept of the dynamic chain, which is how human holds and how manipulates the heavy objects, and then actually it allows us to learn to manipulate very heavy objects like this super huge trash can. Our manipulation rather than just learning from the scratch. This allow us to learn from human demonstration and provides much more efficient manipulation policy. In addition, the same policy can be also a similar approach can be applied to manipulation of the chairs. Here we use them to use it to simulate not simulate the rearrange the chair to the nice positions. All right, so that is about the motion captures, how we learn the interactive motor skills from their human motion data. And now I would like to move on to the next section about the foundation motor. But even before that, I would like to actually just share one of the earliest work, the iterative training of dynamic skills inspired by human coaching techniques, which is actually the work work done when I was PhD student here. So here, the key idea is that this virtual human is trying to learn the motor skills, but guided with some template-based command. At this time, we didn't have any of the large language model. It was like a 2014, and actually work was mostly done in 2013, which means that we didn't have a large language model. So we used some template, and but it has nice interpretation module of the to learn from the incorporate the human suggestions, and then tries to learn the nice athletic motor skills. I would like to refer this as the superhuman motor skills because I cannot do this skill by myself. So, all right. This was nice, but then my point here is that okay, the maybe robots or the virtual human can learn from the some sort of oracle, pretty generic human knowledge. That's the some statement I would like to make here. And then we have preference optimization here. So similarly, the user feedback can be leveraged for optimizing assistive devices such as the exoskeletons. You can imagine this as some sort of the YouTube search or for the exoskeleton. We have nice touch interface, and then user selects which one does he like, A or B, just to select it, and then based on the preference, the algorithm finds the next candidates, how the exoskeleton controller should be adapted. And then it uses the internally, it uses the RAGnet, which learns the models the user preference from the small set of the motion capture data, small set of the preference data, and then suggest the best best parameter for the as the next candidate. And then this system allows the intuitive selection for users, and it successfully finds the optimal control parameter for exoskeleton from the handful of user feedbacks, and it converges really nicely. So this was actually the introduced in the science robotics in 2023. From here, we start to investigate more and more foundational models. Here's the work we done for the basically generating language instruction and policy learning by leveraging foundational models. We first, there's some language command, and then we generate the prompt, and then we generate the human motion using the VQVAE. We generate the human motion, and then we retarget the human motion. And then we use this as the guidance for learning imitation policy. And then, so basically what we can do is from the simple language keyword like a celebrate, or there are other commands like a hop forward from these simple commands. We were able to train the the motion policy. I think it would be super cool if we were able to deploy this onto the hardware, but at that time the student was graduated, so we needed to stop the project. All right, then I would like to move on to next project, the ASC, the Adaptive Skill Coordination. So here, our goal is mobile manipulation. We know the rough location of the objects, and then robot needs to move there, and they relocate the object into the target receptacle. And this is actually, if you imagine that this is naturally a long horizon task. So we first learn specialized experts for the navigation, grasping, and place using some specialized the simulator for each motor skill. And then we learn how to coordinate them by learning the corrective and the coordination network, which is basically follows the concept of the hierarchical reinforcement learning. Right, the concept itself is actually not too groundbreaking, but it gives us super robust performance. It can navigate to the target position robustly, even when there's a dynamic perturbation. Same for the and also if human blocks it, it still tries its best to go to the target location. It checks if even checks if there's other hallway behind the back. Also, if we perturb the object, then rather than just try to grasp it, it keep adjusting its position unless it's sure that it can grasp the object. All right. Then so this is not about the foundational model. This is just the training a robust policy. Then why I talked about this? Once you have nice, robust, low-level motor skills, it can be easily connected to foundational model like the LSC, language guided skill coordination. So we use the audio to text model to generate a library of the skills. and then it executes it. So basically, we implement a high-level natural language-based interface for the previous ASC project. But then the result was very nice. For instance, you can ask it to bring me the chocolate box, cereal box, and peanut butter, and put them on the bedroom table like this, and then it tries to grasp everything and place them on the target location. So here, at the era of the large language model, still I believe that there's a huge need for robust low-level control policy. All right, this is the work done also with my colleague, Professor Danfei Su. We scale up the mobile manipulation learning. Here, the key idea is that we leverage the human demonstration. So we leverage the human demonstration rather than just using the teleoperation, because human demonstration is much cheaper and easy to collect. So in this project, our mobile manipulator robot can grasp the object and move on to the new location. And it's actually even better than the mobile Aloha, because it requires the less robot data. It can be applied to the different tests, such as the wine pouring, wine handover, and then even human is standing on different location, or they even move around. You can still find the human and hand over the wine. All right, so next project I would like to discuss is object navigation. Here, the key idea is to find the object without map information. Then our VRFM allow us to navigate the environments and find the given objects. And such as it doesn't need the map. Basically, it looks around and find the most promising direction, and search that direction until it finds the target position. So basically, this cannot be done if it does not have good understanding of the surroundings. For instance, but think about this: if someone asks you to find the toilet, then probably you walk down the hallway and see if there's a water fountain, which is a good sign for their finding the toilet. So we wanted to implement such a mechanism. How we were able to do that? We leveraged the foundation model called the blip, which basically measures the alignment of the text prompt and the image. And our text prompt was something like oh, there look like a bed ahead in this image. And then if we feel like, oh, okay, if the text and the image align very well, that's a promising direction. And if they are not aligned, then there is another very promising direction. But this nice strategy allow us to give us pretty amazing performance. And then we were able to we awarded the best cognitive paper at ICRA 2024. All right, this was nice accomplishment, but then it's not perfect, because it does not have good understanding of the Pistadia that is very noisy. See, we have these two figures, and then alignment score is like a right-hand side is higher alignment score, like 0.123. It's slightly better than left-hand side. But think about it. Is it really better front here? I don't think so, because it's dead end. Probably we look around it and then, oh no, it's not the good good location, a good direction to find, because we know that it's dead end. Probably we do not want to find anything in that direction. So we want to develop something more toward the physical AI. We want to tune the VLM, visual language model, for the this object navigation scenario. We like just like VLFM, we use the frontier map and select the best frontier with a foundational model. But previously, we used the pre-trained BLIP2 model, which measures the alignment between the given image and the text prompt. On the other hand, key idea of this new project is that we replace that part into the large language model, and we fine tune it on the given data set. So we call this as the film nav. From the here, it's like the solving the quiz. From here, the goal is to find the gravity chair, which is the give us the context, and from the image tokens A, B, and C and D, which one is the most promising direction? We need to answer that multiple choice question in this problem. And then we collect the data, we fine tune the pre-trained VLM model, and then we were able to achieve the nice performance. And here, really interesting thing is that by co-training on the auxiliary task, like a given trajectory video and the relative XY coordinate, which image choice was taken at that coordinate, this gives us a better understanding of the spatial, better understanding about the layout. It's kind of like this. This is the input trajectory. We provide this video to VLM and ask it, this is the input trajectory video. And then we ask our large language model to ask which one is located at the minus 4.8, and then this red one is correct. And then by solving this kind of the auxiliary task, our VLM was able to obtain better concept of understanding about the layout. And then it allow us to have better object goal navigation performance. And it was able to ignore the bad frontier and just directly go to the target. Performance-wise, in our benchmark, it allows the better performance, like compared to the other baselines. And note that it's just not the 3.2% improvements. It leverages the more than 2,000 annotations and the train on the 6 categories in the HM3D data set. And then we were able to achieve this as the almost a zero shot achievement deployment. So in summary, we aim to develop intelligent robot that can make our life better. And then we study optimization, deep learning, and interaction techniques. Thanks for your attention. And let me know if you have any questions.
Thank you, Dr. Hao. It was a fantastic talk. So, uh, it might be a stupid question. So, Professor, when do we think we will actually get to see 22 robots playing soccer?
Oh, that's a little. I think we have. So actually, interesting thing is that if some rich people donate huge pile of money and ask to build a soccer robot, it might only take just I don't know, couple of years, might be.
Oh,
Yeah, we already have I feel like community has good technology, but we just don't do it because it does not give us that much of a thing. And of course, it needs still requires a lot of engineering effort. But I feel like if someone give me enough money, I can solve it within 2 to
So
3 years. I don't know. That's just my promising guess.
these robots, how many eyes do they have?
So sensor-wise, many of the navigation robots, they use both LiDAR and RGBD image. So yeah, that's the most of the setup. But these days, I believe the depth camera already tells a lot of things. But when it comes to semantics, I think the RGB is the most important sensor channel, I believe.
Oh, not the LiDAR.
LiDAR can be useful, but I think the RGBD can also kind of the LiDAR is still useful in some dynamic situation because it provides us the very accurate sensing information. But I think for many slow static motion, we can just use RGBD camera.
Wow. I just think about that. So we do have two different camera. So that's why we can actually
Yep,
see the depth.
exactly.
Yeah. This are they doing same thing?
Some depth camera use the two multiple cameras to estimate the depth, but I think a lot of depth camera uses emits the structured light to estimate the depth.
All right. Is there any question from the participant? Just let me know. You can just anyone? All right. Dr. Ha, thanks for your time and thanks for your fantastic talk. And I hope everyone enjoy your fantastic work and the futuristic insight. Anyway, I'd like to thank our director, Dr. Ha, and director Dr. Yo. So this webinar will continue to introduce our esteemed faculty in the Georgia Tech. So stay in the tune, please. Yeah, thank you,
All right,
Dr.
thank
Ha.
you.
Mhm.